Hi everyone, and welcome to another Planetarium live stream. My name is Jessica, and I am the director of the Planetarium. And with me tonight are a couple of familiar faces, but I'll still let them introduce themselves, starting off with our sea turtle behind you.
Hi, I am Lindsay. I'm a physics graduate student here at UMD.
And I'm Eli. I'm a physics undergraduate student at UMD.
So tonight we are going to be taking you into the animal kingdom and exploring how animals and insects actually use physics concepts. And there's some really cool and interesting ways that they do this. And Lindsay is going to be sharing that with us tonight. Throughout the presentation, if you do have a question, you can always leave it down in the comments below. Eli and I will both be watching those, and we'll try and get to them as we see them. And if we can't get to them right away, we will take time at the end to answer those questions. So with that, I am going to hand it off to Lindsay.
Okay. Okay, so we are talking about Phurry Physics today, how physics comes up in the animal kingdom. And first, we are going to talk about color in the animal kingdom. So first, we kind of need to know just what color is. And so if you have a source of white light, and you separate that white light out using a prism, you get all of the colors of the rainbow out. So each of these colors of the rainbow have different wavelengths and frequencies that result in the color that they have. So we have white light coming in, and then the different frequencies and wavelengths of light interact with this glass prism, and the light gets separated out into the colors. So white light, the important thing to remember here is white light is made up of all of the different colors of the rainbow. So with pigments, so sometimes the color of an animal comes from pigment in its skin or its fur. So in this case, you have sunlight coming in and you have a pigment molecule. In this case, it's in a leaf. And all this pigment molecule takes in all of the colors except for green. So you end up seeing the leaf as green color. So here we have an animal example with a bird. So the feathers, if we take a close-up look at feathers, we have a keratin cortex layer on outer layer, and then pigment granules underneath that. And so we have all of the colors coming in from the sun because the sun is made up of white light. And these red pigment granules end up absorbing all of the colors except for red. And so red gets reflected back out at our eye, and so our bird looks red. Some other animals that are colored by pigment, we have another red pigment with this ladybug right here. Polar bears have white pigment, making them look white. And this frog over here has a yellow pigment in its skin, helping it make or look yellow. Another way that animals can get their color is from structure. So earlier I was showing you how white light enters the glass prism, and the glass prism shape separates out the white light into all of these different colors. So over here, we have an oil slick, and the oil is at different thicknesses. So as the white light comes in and hits the oil slick, depending on the thickness of the oil where the white light is hitting, either blue is going to get reflected, or orange, or red. And so these colors in the oil slick, they're a result of the structure of that oil and the thickness of the oil. So with the birds, we have that keratin cortex layer again still, and then we have a layer of these melanin nodules, another layer of keratin, and then another layer of the melanin nodules. So in this case, what happens is we have the light from the sun. It is all white light, and as the light goes into the keratin cortex and the melanin nodules, it starts to separate out like it did in the prism. Oops. And then as you look at the feathers from different angles, you see different colors. So we have the white light coming in. It gets separated out into all the different colors of the rainbow. This, if we are viewing from this angle, we end up seeing the feather as purple. If we end up viewing from this angle, then we have the feather looking blue. And if we view from this angle, we end up having the feather look green. So the thing with this color from structure, and this is what causes iridescence, is that the color changes based on your viewing angle of the feather. So this is another example of an iridescent animal. It's a snake, and it has iridescent, or it has structures in its scales to make it look iridescent, like the bird was. Another way that animals can get color from structure, and this is non-iridescent color, is just from a kind of keratin air matrix. So for this bird's feathers, we have a keratin layer, then we have this spongy layer of keratin and air, and then the black melanin layer at the bottom. So in this case, we have the sun's light coming in, all the colors of the rainbow. All of the light, gets separated out into the different colors. But this keratin air matrix, only the structure is set up such that it only reflects blue light, the wavelength and frequency that blue light is. And all of these other colors end up get absorbed by the black melanin layer. So this bird is guided by this keratin air matrix. So we have, here are some other blue animals, and actually it's really uncommon to find blue pigments in the animal kingdom. So usually when you find blue things out in the animal kingdom, it's because of this color from structure. They appear blue because the structure of their wings or feathers are reflecting the blue light because of the structure of the inner structures of the feathers and wings. This also applies to humans. So human eyes, if you have brown eyes, you actually have brown pigment in your irises. But if you have blue eyes or green eyes, you don't have green pigment or blue pigment in your irises. The structure of your iris actually makes it so that the light going through your iris reflects the blue light coming from the sun, or the green light, depending if, again, if you have blue eyes or green eyes. So yeah, no blue pigments or green pigments in the blue eyes or the green eyes, which I think is kind of cool. Okay, so another way that animals can kind of get color is by interacting with ultraviolet light. So the sun, I'm not sure what happened. Sorry, I lost my screen. Do you guys still see my presentation?
I do not. I see your MyU login.
Yeah, we're on your like Google page.
What happened?
Do you want to stop share and reshare?
Is that good?
No, I still don't see it.
You're back on slides now, but it's not like sharing, or it's not like full screen.
Oh, there it goes.
There we go.
Weird. Sorry about that. So the sun has the white light made up of all of the different colors of the rainbow, but also it has other types of light coming from it also, like infrared and ultraviolet light. So in this example, we have the ultraviolet light coming from the sun. It is being absorbed by some type of material, and then it is emitting lower energy light waves. So we can't actually see ultraviolet light, but after it gets absorbed by a certain material, the lower energy light wave that is then emitted, we can see that. An example of where this happens in the animal kingdom is actually in coral. So we have the sunlight interacting with the coral, and the ultraviolet light gets absorbed by the coral and then emits visible light. We're not really sure why the coral does this. It's possible that the coral kind of uses this as a way to kind of protect itself against the sun. So it has a way, again, of absorbing those ultraviolet light from the sun as it is then emitting the visible light. Another animal that does this is the scorpion. So we have that sunlight coming in, the UV light getting absorbed by the scorpion's shell, and then visible light being emitted back out. Again, we're not sure why the scorpion does this. It could also be due to, because of sun protection, like we think is happening with the coral. So it's getting protected by the sun from the sun because it is absorbing the ultraviolet light from the sun. It could also be for mating, or it could also be for kind of help with their sensory. They don't have very good eyesight. And so if half of the scorpion is like under a rock or in shade, and the rest of the scorpion is kind of out, not in the shade, it can't really tell because it has such poor eyesight. And so that means that it cannot, it would not be able to hide from predators very well due to its poor eyesight. So it's possible that this, the fact that it's absorbing the ultraviolet light is kind of helping it sense if it is in sunlight or not, or if it's in full shade or not. So it will know that if it's not under full shade, because the rest, let's say half of it is absorbing that ultraviolet light from the sun, that it needs to move more into the shade to avoid those predators. Another way that animals can get color is through bioluminescence. So in this case, we have light interacting with a chemical in the cells of these animals, and then emitting light. And so here we have a animal that ends up making a blue light. But it can be for it can be in lots of different colors and also for a lot of different reasons. The light can be used to startle things, cause misdirection for other animals, or to be distracting. It can be used as kind of an alarm system. It can also be used as a warning for other animals. It can also be used as a lure. So this is in the movie Finding Nemo. The fish turns on its light, and then it kind of lures in the dory. And so that's one way that this light can be used, or it can also be used to illuminate their prey or stun and confuse prey. There can also be bioluminescence for mate attraction. So lots of different reasons that these animals, especially in the lower parts of the ocean where the sunlight doesn't usually go, lots of different reasons for them to light up in bioluminescence. Okay.
So we got a question. We got, does the fluorescence help the scorpion know how to detect other predators?
Oh, that's a good question. I guess if like the predator kind of came over the scorpion and was blocking the sun, then the scorpion would probably know that there's a predator over the top of it blocking the sun from getting to it. So that's probably one way that it could actually, sense predators. Okay, on to magnetoreception. So moving away from color. So this video is kind of going to explain what magnetoreception is and how animals can use it.
Imagine waking up on the beach before dawn. The glimmer of light leads you to the shoreline. Suddenly, a wave pulls you in. At first, you use the direction of the waves to guide you. But once you're in the open sea, with powerful currents bombarding you, and very little light, how can you be sure of where you are and where you're going? For a hatchling sea turtle, the answer is magnetoreception. That's the ability to sense magnetic fields. We know many animals use this sixth sense for navigation. What we don't know is exactly how magnetoreception works. Here's what we do know. Earth itself is like a giant magnet. The motion from its liquid outer core generates a magnetic field. Certain animals can sense this field and use it as a compass to tell them if they're heading in the right direction, and a map to give them signposts along the way.
There's two competing theories for how magnetoreception works. One is a chemical sensor, the other is a mechanical sensor.
The first theory is that animals have tiny magnetite particles in their bodies that act as magnetic receptors. Magnetite is the most magnetic natural metal on Earth. It's been found in many animals that exhibit magnetoreception.
And it's thought that it's the only potential sensor that would be sensitive enough to capture these incredibly tiny variations in magnetic field strength that would allow the animal to not just know whether they're going north or south along the magnetic field line, but know the precise beach that they need to get to.
The other theory is that animals possess a protein in their eyes called cryptochrome, which allows them to see magnetic fields. Cryptochrome has been found in the eyes of several migratory birds, but we haven't proven either theory for a few reasons.
With magnetoreception, you don't know where to look. Magnetic fields pass invisibly through the entire body, so researchers don't know exactly where these magnetite particles or cryptochromes would be attached to particular cells. So mistakes are made all the time.
And so far, cryptochrome experiments have only yielded positive results in the presence of magnetic fields much stronger than Earth's.
The frontier is now not so much at the animal behavior level, but actually getting inside the brains of these animals and trying to find these sensing cells and connecting them to the neural circuitry. It's not so much a question of which animals have this sense, but which don't. So researchers have said, well, why not humans? Maybe we had this sense at one point deep in our evolutionary past and lost it, but maybe there's a vestige left. Researchers in California and Japan have gone after this holy grail one more time with a very specialized experiment, one that relies on double blinding and magnetic shielding, and they're seeing glimmers, maybe even more than glimmers, of this magnetic sense in humans. It's starting to be reproducible, and they're really excited about it.
So we saw a few different animals that we are pretty sure use magnetoreception to kind of navigate. These are some other ones. We have the naked mole rat that uses magnetoreception, a homing pigeon, and also the honeybee. Also, one of my favorites is actually the fox, which uses magnetoreception to help it hunt and catch prey.
It's just so cool.
Oh, I love this one with the fox. And they're not only using the magnetic field to kind of help them align to the north to help them get their prey, but they're also using physics in catching the prey because they are using projectile motion and doing some physics calculations in their head to make sure their projectile motion is the right height, right distance to get that mouse. So yeah, foxes really are just amazing physicists. So some other animals can navigate using star patterns. So this bird is called the wild-caught Indian bunting. So this bird, migrates from north to south at a certain point during the year. And researchers are curious to see if this bird knew which way was south due to perhaps, being able to detect the magnetic field like the animals that we were just looking at, or if maybe they were able to see detect the star patterns that were in the southern sky and follow those. And so to figure this out, they actually caught a bunch of these birds and put them in a planetarium and then put the constellations up on the ceiling. And they found that the birds went towards the patterns that make up the constellations in the southern sky. And so, yeah, these birds, they don't actually use that magnetoreception to know if they're going south, but they can recognize the star patterns in the southern sky and follow those. This dung beetle, it doesn't have super great eyesight, and it needs to take these giant balls of dung in many very long distances, but it needs to make sure that it is traveling in a straight line so that it does not end up where it started. And so to make sure that it is going in a straight line, it actually looks at the brightest part of the night sky, which is usually the Milky Way. So it follows the bright patch in the sky of the Milky Way and follows that to help it travel in a straight line. There are also some animals that can walk on water. So water tension is kind of specific to water because of the way that water molecules are. They're what's called polar molecules. And so one side of the molecule has a negative charge and the other side it has a positive charge. And because of that, they kind of interact in interesting ways. And so when water goes on a leaf, for instance, it doesn't just flatten out. It actually makes this kind of ball of water due to the water tension caused by the kind of weird water molecules that are polar. And so here we have a spider that actually is on top of water, can walk on water. So you can see kind of the water bowing out a little bit or underneath this foot. So the spider's feet do not provide enough force to actually punch through the surface of the water. The surface tension provided by the water helps keep the spider on the surface of the water. Okay, lastly, we're going to talk about sound and how some animals produce their sound. So here we have a cricket. It has a kind of harp shape on two of its wings and a file on one wing and a scraper on its other wing. And then it just kind of rubs the scraper on top of the file. And then that is how it makes its cricket sound. The club-winged manakin is pretty cool. It kind of has a similar thing going on to make its sound, where we have one wing kind of rubbing against the other. But the cool thing about this animal is that it actually beats its wings together 107 times per second. So that's pretty crazy. Another way that animals can use sound is with echolocation. So here we have a bat. It emits a sonar signal, which is sound wave. And if there's an object out here, that object will, or the sound waves will bounce off of that object and go back to the bat. So the bat will know if there's an object there or not by if it gets sound waves heading back towards it.
Think of a cat silently stalking a bird, or a rattlesnake ready to ambush a mouse without rustling a leaf on the forest floor. An owl can swoop down on a mouse without making a sound. Silence is the cloaking device predators use to capture a meal. Now consider bats, whales, dolphins, porpoises, and a few other animals that use their voices to find prey. Through echolocation, these animals emit sounds of different frequencies and loudness that bounce off the objects around them. The echoes are then captured by the ears, and the brain figures out how to recognize food and navigate the surroundings from those signals. Some bats emit sound blasts that are so loud they could deafen human hearing. Only we cannot hear their ultrasonic voices. The world would sound quite different if we could. Like whales and dolphins that use echolocation in water, bats use their voices to see the world through air, and very effectively. A katydid rests motionless on a leaf, one of thousands of leaves on a tree. The insect doesn't make a peep. The night is black. A leaf-nosed bat flying nearby blasts the tree with sonar at ultrasound frequency, then listens. It sees the katydid with the echo created from sonar and swoops in for the kill. No human-made sonar equipment can detect objects with such finesse. In fact, the most sophisticated submarine sonar system, large as a house, cannot see the world nearly as well as a bat. Leaf-nosed bats are at the pinnacle of echolocating animals. Their fleshy noses are like musical instruments that amplify and focus the sounds made with their larynx. In fact, their noses change shape to produce different sounds for scanning different objects in the surroundings. Their ears are also capable of shape-shifting to capture the sensory information they need at any moment, so they can fly in the dark without hitting tree limbs or power lines, communicate with each other, and pick an insect meal from dense vegetation with surgical precision.
All right, so that is all of the different ways, at least today, that I talked about all that I could get to today to that, oh my gosh, that the animals use physics. There's a lot of different ways, even more than what I talked about today, that animals use physics.
So we got one more question. Can the water be too deep for the spider to safely walk on it?
I think with that, it has more to do with the, so this surface tension can happen no matter how deep the water is. So this is just an interaction that the spider has with the surface of the water and the water molecules at the very surface. Yeah, so this can happen with any depth of water.
Would you say it's kind of analogous to like having something balance on like cling film over a bowl? Or like
Yeah.
if you have enough force that you puncture the cling film, you'll fall through. But if you're able to spread out that weight and that force, then you don't punch through it. And so the surface tension acts a lot like that.
Yeah.
All right. If there are any other questions, please let us know down in the comments. One thing that I thought about that I think is kind of interesting to think about is how light pollution is playing a part in affecting these animals that use the stars to navigate. Because, I mean, it's not just hurting us in our view, but if they can't see the stars, then, you know, they're going to get lost too.
Mm-hmm. Yeah.
And so there's a lot of other ways that you may not realize that we are having a negative impact on the animal kingdom. And so trying to do things like minimize light pollution is not just for our own benefit, but there's a lot of other benefits as well. So just something we like to keep everyone informed and thinking about. We very much support minimizing light pollution efforts and keeping our skies dark for as much as we can. All right. So let me, while we see if any other comments do come in, tell you what's coming up. So on Saturday, we are going to take you on a tour of some really cool objects in our universe called Messier objects. So we'll tell you kind of what those are, what the different types of objects are, and give you some cool ones that you can find yourself. Some can even be seen with your naked eye. You don't need a telescope for those. And there are some really good ones up in the winter, and so we'll tell you all about that. And then next week, and I realized I did not load my promo images for next week, but next Wednesday we're going to be doing a special show called Starry Birds of Inauguration, since next Wednesday is Inauguration Day, and that word actually is has its roots in kind of telling fortunes through birds, or like telling omens through birds. This is something that Jim Rock was actually sharing with us the other day, and so he's going to be putting together kind of a cool presentation on these starry birds, these bird constellations that are found in many different cultural skies, and how these birds kind of played a part in forecasting predictions and things, many which were used for like whether the new leader was going to be good or bad or not. There's some really cool stuff. I'm excited to see what it all comes together with. And then next Saturday, we'll be doing another edition of Ask an Astronomer. So we'll be here to answer any and all of your questions that you have. We like doing these. It's a lot of fun. A few other things. If you didn't know, we are offering private virtual shows now, including virtual field trips. You can find information about that on our website. And we still have some of our Stellar Distancing t-shirts for sale as well. That is helping us to raise money since we have been closed since mid-March. I can't believe we're rounding close to a year of being closed, and that did not expect that. It's funny, when I was on campus the other day, I saw the sign that I made for the planetarium that said closed through April, because that's what I thought we would be doing. And little did I know that may actually have just meant closed through next April. But we're hoping to be able to open soon. Maybe not soon, but we're definitely eagerly awaiting when we can safely reopen. But as we do have a very small space, we want to make sure that we keep our staff and community safe. So we will open once it is safe to have people back. But we're excited for that day. Until then, though, keep joining us here in these live streams. We will continue to do these until we are back open for normal operations. All right. So I'm not seeing any other questions. Eli, are you seeing any more?
Nope, just a thank you.
All right. Well, thank you, Lindsay, for sharing all of this really cool stuff with us. Thank you, everyone, for joining us tonight. We hope you have a wonderful rest of your day, and we will hopefully see you next time. So until then, bye, everyone.